Thank you very much for the kind introduction. Today I will give a very short presentation on our new system, a long-term stable thulium-doped fiber chip pulse amplification system with more than 100 watt of average power and more than 1 gigawatt of peak power. Ultrafast lasers find many uses in industry, biomedical applications, and also fundamental research. And the most demanding applications require extremely high intensities, which can be reached with ultrafast lasers that emit energetic pulses with excellent spatial beam quality to allow for tight focusing. Simultaneously, a high pulse repetition frequency is often desired for short acquisition times and high contrast measurements. And these demanding parameters, however, are currently only provided by lasers with an emission wavelength at around 1 micrometer. The emission wavelengths, however, can be the key to many new application fields, since it is one central aspect on the nature of light-matter interactions. There are currently two main strategies for achieving sufficient performance in the different wavelength regimes. The first are large-scale facilities, like synchrotrons, which are expensive and quite limited in accessibility. The second is laser-driven nonlinear frequency conversion, with prominent examples being difference frequency generation and high harmonic generation. It is known that these conversion schemes can benefit from ultrafast lasers with longer wavelengths, which constitutes a strong demand for their power scaling and availability of commercial turnkey systems. It is the mission of active fiber systems to provide a rapid transition from research into reliable, commercially available systems. Our main market is fundamental research, material processing, and life science. Today, we are the technological leader for high-power ultrafast fiber lasers, and we are a rapidly growing company. We have many different systems, and if you're interested in this, I would like to invite you to come to our website and check it out. So there are many platforms and also several add-ons like fuse cycle generation, carrier envelope phase stabilization, or even XUV sources or optical parametric amplifiers, which provide great tunability in different wavelength regimes. The concept of our company is based on fiber amplifiers, obviously. And the advantages of fiber amplifiers and lasers are typically the fractional emitted beam quality, high efficiency, and excellent heat dissipation. However, due to the long interaction length in the fiber core, we have also to face some challenges like nonlinear effects. And these challenges can be mitigated, for example, by means of chip pulse amplification, the use of short, large core fibers that still provide single mode beam quality. And one of our main techniques also is the coherent combination of multiple amplifiers. Here, we start with a beam from the front end, which is divided into multiple amplification channels. And the optical path length in each channel can be actively controlled, such that the constructive interference is achieved in the combining stage after the amplification process. By doing that, the output power can be scaled by nearly the number of channels, thereby overcoming the limitations which are set by a single amplifier. And since many of our systems are typically based on 1 micrometer wavelengths, by doping the core of the fiber amplifier with the terbium. Now, we would like to go to longer wavelengths, and this is why we chose a different dopant, in this case thulium, which can provide emission at around 2 micrometer wavelengths. This sounds quite easy. In fact, it's not. I will come to this a little bit later. Our thulium-based products can offer up to 3 millijoule and 3 millijoule pulse energy, 300 watt of average power, and less than 150 femtosecond pulse duration. And it provides a great alternative to 1 micrometer systems, which are, for example, used to pump optical parametric amplifiers towards 2 micrometer region. We use those lasers to generate, for example, mid-infrared radiation in between 5 and 18 micrometers, or we can use them to generate, for example, water window harmonic generations. And what sounds quite simple is actually not. So ultrafast thulium-doped fiber lasers are not much more than a laboratory curiosity. And only recently we have made some significant progress in power scaling those systems. And the problems come typically with the availability of suitable high power optics. So as you can see in this image, you can have thermal heating of those optics. And another problem is the expensive and sometimes low brightness availability of 790 nanometer laser diodes for optical pumping. So when you look at the properties of thulium-doped fused silica, you can recognize that we have a very broad amplification bandwidth in the 2 micrometer wavelength region, which can be used to amplify pulses with a bandwidth that is sufficient for sub 100 femtosecond pulse duration. However, due to the pumping at 790 nanometers, we have a quite large quantum defect, which can lead to strong heating of the fiber amplifier. However, there is one effect, which is quite nice, which is called cross-relaxation, which can significantly enhance the efficiency of the fiber amplifier. Here, one pump photon can lead to the simultaneous excitation of 2 thulium ions, in principle doubling the quantum efficiency. Thereby, we can achieve efficiencies of around 70% in optimized fiber amplifiers. However, this is a laser physical challenge. So if you want to exploit cross-relaxation, you need optimized fibers, and you also need to follow some experimental guidelines. So you need an advanced cooling concept, and you need sufficient seed power in order to achieve this. There are some more problems when you go to the 2 micrometer wavelength regime. For example, the atmospheric absorption due to the water vapor in the atmosphere, which can lead to bad beam quality and also bad pulse quality. In order to mitigate this, it's recommended to go into vacuum in those free space sections of the system. Here you can see a simple sketch of how our system is built. So we start with an oscillator, and then we have a preamplification chain, which is all fiber and includes a stretcher, its pulse picking device, and we also introduce some pulse shaping here in order to mitigate nonlinear effects. Then we have a series of 4 main amplifiers, which are all free space pumped, and also the signal is coupled in free space. In this case, we put these amplifiers also in vacuum. And then we have the compressor in order to achieve ultra-fast operation of our system. This compressor is also placed into a vacuum chamber in order to mitigate those absorption effects in the atmosphere. Some more specifications about our front end. So we have pulse repetition frequencies between 25 kilohertz and 25 megahertz, a spectral bandwidth which is sufficient to amplify or compress pulses down to 110 femtoseconds, which is the Fourier limit, and we have a stretched pulse duration of around 700 picoseconds in our system. The 4 main amplifier channels are based on thulium-doped photonic crystal fibers, which provide efficient amplification of more than 50% slope efficiency. And by using an advanced cooling concept, we can provide for excellent long-term stability. And in this case, you see we can amplify to more than 120 watts with a single amplifier. Here you can see on the left picture the compressor in vacuum, which is used to circumvent those water vapor limitations. On the right side, you can see that even at very high output power of more than 120 watts, we achieve excellent beam quality with a measured m² value of 1.1. We use highly reflective dielectric gratings, which allows us to achieve a compressor efficiency of more than 89%. And due to the fact that our thulium-doped photonic crystal fiber is a polarization maintaining concept, we also achieve a very high polarization extinction ratio after amplification of more than 20 dB, which allows us for very high combining efficiency of 95%. So after compression, we reached more than 200 microjoule pulse energy, more than 120 watts of average power, and less than 120 femtosecond of pulse duration. In fact, here we have 111 femtosecond pulse duration. And all this at the center wavelength of around 1940 nanometers. We have measured and tested the systems over a long period of time, in this case of more than 90 hours. And you can see that we reached a very good standard deviation of 0.14%, so it's a very stable system. And also the beam stability is excellent in the system. So these are excellent prerequisites for nonlinear pulse compression in fibers, for example, to the fuse cycle regime. And if we do that, we can use this system, for example, to generate high flux mid-IR by difference frequency generation. And here you see an example that we can achieve actually brightness, which is significantly higher than the typical flux from synchrotrons in this wavelength regime. We have also done some preliminary testing to generate water window harmonics with our colleagues at the Institute of Applied Physics in Jena. And here you can see that after the Miller mesh, we see that there is a clear absorption edge here. So we have some photons in the water window. And this is an excellent thing because we can use this radiation for coherent diffractive imaging in the water window. And by increasing the flux further, we can significantly reduce the acquisition times here. So what are the prospects of these systems? So based on the current design, we can actually scale the output energy to more than 500 microjoule, for example, by introducing some phase shaping to our system. And by increasing the pump power, we can reach more than 200 watts of average power after pulse compression. And if we go to a different fiber design, to larger core diameters, we can scale the output energy to more than 3 millijoules at average powers of more than 300 watts. And of course, you can always go to more channels. So this is indeed scalable to the 10 millijoule range and even kilowatt average power. And of course, we are working on the fuse cycle generation, as I've already mentioned. So we intend to compress the pulses to less than 20 femtoseconds to the fuse cycle regime, and this at a very high average powers of more than 100 watts, based on anti-resonant hollow core fibers. And with this, I would like to thank you for your attention. I'm happy to answer all your questions.